Lastly, before we get into the discharging phase, we want to take a look at the voltage across the resistor. And as we said, the voltage across the resistor is the current in the circuit, in this case that series circuit, IC of t or IS of t times the resistance, which becomes IC of t times 8,000, which was 8 k ohms. And then that turns into 8,000 times our IC of t, which is shown here. IC of t times 2.5 milliamps. We just multiply those together to give us this constant out there, and it's 20 volts. And hopefully that looks familiar, because at t equal to 0, when that capacitor is a short circuit, right there, all the voltage drop right at that split second of time is across the resistor. So we get a 20 volt, and in this case, because that current can change instantaneously on that capacitor, we get a 20 volt spike across that resistor. Okay, so now we're starting to see from an electrical standpoint where voltage spikes and things, current spikes and things like that can result. And it's true, it's because of inductance and capacitance that's in our circuits. Okay, then I went ahead over here and calculated, plugged in 1 tau, 2 tau, 3 tau, 4 tau, and 5 tau, and calculated the voltages, and so we'll go ahead and graph that. And I think if I did this right, I had, this was 5, 10, 15, 20. So this is 20. That would be 5 volts. So that would be 7.5. So we're a little bit less than, after one time constant, a little bit less than 7.5 volts. Then we drop down to a little more than 2.5. And then we're, after 3 time constants, we're less than 1, which would be, let's see, 5, 2.5, clear down here. And again, that thing asymptotically approaches then the horizontal axis, or 0 volts. Let's not lose sight that that thing is decaying. That's the voltage across the resistor decaying out to 0 volts. Okay, now that was all the charging circuit. Let's go back and look and see what happens when we go to discharge, what we call discharge that capacitor. So let's go back to our original circuit. Okay, so now we're going to take a look at, we're going to get to discharging of this capacitor. But before we do that, let's just take our circuit out of this dynamic state for just a moment. And what I mean by that is I have switched that switch to position 2. And as long as there's no current allowed to flow, theoretically what will happen is, if you recall from the charging circuit, the voltage on the capacitor has charged up to 20 volts. And we are beyond, let's say, any time past 5 tau, or if you remember, 5 tau was 5 times 96 milliseconds, or 480 milliseconds, or 0.48 seconds. So anytime after a half a second, now think about that, that's, less than a blink of an eye, right? So this is not a very fast acting circuit, okay? But it is very dynamic. And so what's going to happen is we are going to take this switch and we're going to put it in this state, in position 3. And what happens is now our capacitor now will discharge. We're going to have ICT. Now I'm going to call it negative, because it is, to me, the way I look at it is that capacitor will hold that charge. An ideal capacitor would hold that charge for infinity, okay? But until we give it the ability to discharge. And remember I said that the current can reverse, okay? Or it can change instantaneously in a capacitor. And that's what's going to happen. So what this thing, another way to look at this is, let's just take a look as if that capacitor was a battery. And so at the moment I change the position of that switch from position 2 to position 3, let's stop time at that moment in time, and we end up with what to me looks like a 20 volt circuit with a 20 volt supply. Let me put our switch in there. But when I move that switch, you got to remember, now we have an 8K ohm resistor and a 20K ohm resistor. And we have a new tau. Okay? And tau is now RTC, or 8,000. I noticed that I had that resistor wrong. At 20K ohm, it should have been 12K ohm. So it's 8,000 plus 12K, or 12,000. That gives us 20K ohms times C times 12 microfarads. And now tau is, when I take that calculation, I get 0.2 0.24 seconds, or 240 milliseconds. Now that's 1 tau. Alright, so now our 1 tau on our timeline out here, then, this would have been 480 milliseconds. If I add one more tau of the new tau to that, that would be 480 plus 240. This time now is 0.72, or 720 milliseconds. Okay, now we have a new tau. So here we had, in this first 5 tau, we had, let's call it tau 1, where it's 96 milliseconds, and now tau 2 is 240 milliseconds. Okay, but as we said, the current can reverse instantaneously. What's going to happen is the current is going to reverse instantaneously at this point when we close that switch. So let's say we close the switch to position 3 right at 5 tau. Okay, that current will reverse and we'll get a spike in the other direction. Now the question is how high is that spike? But it's also going to decay, and it's going to go back to 0, so it's just like that. Okay, and I'll explain what that formula is in a second. But before we do that, let's calculate what is that current. Well, that current IC is going to be 20 volts over 8,000 plus 12,000. So it's not as high, and that peak current is going to be 1 milliamp. So instantaneously, it's going to go from 0, where it had reached in a steady state, to a peak of negative 1 milliamps in the opposite direction. So you can see the dynamic capabilities of electric circuits that we're beginning to introduce here. Okay. Now, that discharge circuit is going to be that discharging current is going to behave just like the charging current, where we had IC of T equal to E over R, which we just calculated, e to the negative t over tau. You just got to remember now that this tau is 240 milliseconds. So it decays at a faster rate. And what I should probably do is make that line a little more steep, because it's going to go a lot quicker. Okay? And the voltage on the capacitor now, so we're headed for now, in the discharging circuit, what we're going to do is we're going to discharge the voltage on the capacitor is going to completely discharge. We're not charging to the open circuit voltage, okay? When our capacitor discharges, there's going to be no voltage in the circuit at the end of the discharge phase. So V steady state now, or V, now we don't call it open circuit, but at the end of now 5, let me call it tau 2, is going to be equal to 0 volts. So this thing is going to discharge from 20 volts down to 0. And what ends up happening is this becomes VC times that decay function, negative t over tau, when it discharges. So it's going to be 20 e to the negative t over tau. And so the voltage up here is going to do something like this. It's going to happen quicker because tau is I'm sorry, I got that wrong. It's going to happen longer. The current is going to take longer. Okay? And the discharge of the voltage is going to take longer. So it's going to be less steep. Okay? But we could still count off those 5 tau. 5 tau 2. Clear on here. And we'll be back where we started.